Hello and welcome back to Maths with Mr. Duffield. I am the aforementioned Mr. Duffield with a little bit more Deputy Grecian's work, requested help on some of the Easter exam practice that you were set. So let's begin. Question 2 is the specific question that's been asked for help with. Curve C has equation y equals 8 minus 2 to the power of x minus 1, where x ranges between 0 and 4. Complete the table below with the value of y corresponding to x equals 1. So the only real element of this first part is to replace x in this equation with 1. So y becomes 8 minus 2 to the power of 1 minus 1, which is 0, yeah? So that becomes 8 minus, well, anything to the power of 0 is 1, which is 7. Part A finished, nice and quick. Part B, that's where issues began arising for at least one of us. Using the trapezium rule with all rules of y in the completed table, find an approximate value for the integral of 8 minus 2 to the power of x minus 1 with respect to x. Now, a specific integral, just by way of reminder, effectively gives us the area between the curve and the x-axis. So this entire space underneath this graph, if I just vaguely shade it in like that, this entire space for this whole area is found by integrating this algebra and then substituting in the upper value, in this case 4, and subtracting the lower value, in this case 0. And having done that, we get the area underneath the curve. Now, it's a bit tricky to integrate that, so that using the trapezium rule makes a bit of sense. Now, as a reminder, the trapezium rule, in short, is effectively done by splitting up all of this area into vertical strips and effectively making those strips into individual trapezia, finding the area of each of those trapezia and adding it all together. Clue in the name, trapezium rule. Now, how wide are my strips going to be? Well, my table here ranges between 0 and 4 with gaps of 1 between each strip. So let's split that up in that like manner. 1, 2, 3, 4. I apologize because obviously these strips they're not perfectly evenly spaced, but you get the gist. Effectively, I'm splitting apart this area into strips by which each of them can effectively be considered as trapezia of this height and this height, effectively making a straight edge there. Similarly, over here forms a trapezia straight, and here straight line joining these 2 points. And actually the last trapezium isn't actually a trapezium at all, it's a triangle. But you see that by adding these straight lines and physically representing what's happening, I'm going to get an estimate by finding the area of each of these trapezia and adding them all together, but it's going to be an underestimate, isn't it? It will be less than the actual area underneath because these straight lines cut underneath where the curve actually runs. Okay? So, with that done, with the trapezium kind of strips set up, we need to work out some distances. Well, the gap between each of these ranges is 1. That gives us one of the dimensions of these trapezia. And then we need to know the heights. And to find out the heights of each of these trapezia, we're going to use the y values. So the height of this first one, 7.5 here, and then over here, this point is 7 high. I get that from that point of the table. 1 across, 7 up, and then 2 across, 6 up. So the height here is 6, and then similarly copying across the rest. 4 here, and obviously down at the base of this triangle is 0. The rest of the question is just using this height and this height to find the area of this trapezium, this height and this height to find the area of this trapezium, this height and this height to find the area of this trapezium, and then finding the area of this triangle at the bottom, adding it all together, and then we've effectively found the area. So, just as a reminder, when we're finding the area of a trapezium, it might look something like this. let's say that this is 7.5. Let's see that that's 7 and that's 1. We find the area of a trapezium like that by adding together both the parallel side lengths and then multiplying the result by the perpendicular sort of breadth of the shape. Okay, 7.5 plus 7 times 1 over 2. So in the case of that first trapezium here, or in other words, this first strip from the graph, we get 7.5 plus 7 effectively divided by 2. That's 7.25. Okay, that's the first strip. The second strip is half of 7 plus 6 times 1. These times 1s are effectively multiplying by these little widths down here. Effectively, it doesn't really mathematically do anything, but yeah, 7 plus 6 over 2. 6.5. Third strip is 1/2 of 6 plus 4 times it by 1 again, and that comes out to 5. And then I've run out of room here, but we can squeeze this bit on. Effectively, the triangle at the end is obviously 1 times 4 divided by 2, which is obviously going to be 2. So we've got 7.25, 6.5, 5 and 2 as the areas of the shapes we've used to represent the kind of number, a rough approximation of the area underneath the curve. So the final answer is adding all of those together. All right, I've got another piece of paper here to work on, and actually there's an awful lot of space given to you to find the eventual answer. You're gonna have to bear with me. 7.25 plus 6.5 plus 5 plus 2. 20.75. That is the trapezium rule, and it is as simple as it gets. I mean, well, I say simple as it gets. It's moderately complicated to visualize, but once you've established those shapes, finding all of their areas is really as simple as just applying the rule of finding the area of a trapezium. It's that straightforward. Now, part C. Use your answer to part B to find an approximate value for the area of R, which is this grey space here. Well, I hope that you can jump onto this more quickly than I can say it. It is the area that we found in the previous part. Subtract the area of this triangle. What are the dimensions of this triangle? 7.5 by 4. Yeah? 7.5 high, because we know what the value of y is where x is 0, and 4 wide, because we know that this curve ranges between 0 and 4. So, for this last little section, the area of R is 20.75 minus the area of that triangle, 7.5 times 4 halved. That's 20.75 minus 15. That 0 looks strange. So, final answer for that is 5.75. There we go. So, to finish this, well, it's a moderately long video, I guess. In order to work out and use the trapezium rule, it's simply a case of splitting up the area underneath a curve into strips. Each strip is considered to be a trapezium. You find out the area of each of those trapezia, add it all together, and then there might be a slight variant involving perhaps finding the area of a triangle and subtracting it from your previous answer. Nothing too overwhelmingly complex about it, really. You just need to know to split it up into trapezia. That's all from me today. I'm going to go home. I wish you all the best with all of the work that you're up to, and for goodness sake, get your work done on Teams. I will talk to you very soon.